Okay, good evening. So let me remind you what we have done last week quickly. Last week, we finished the chapter on, what was it about? On LP spaces. So the thing is, as I said, on LP spaces, you have functions which are not regular. You can change them on some points, it doesn't matter, because you are dealing with equivalence classes. So the last result I mentioned is up to an error of size epsilon, and you can choose epsilon as small as you want. You can always approximate any wild function in LP by a continuous function. But of course, you lose something. But the statement is for any epsilon, for any f in LP, you can find a continuous function also in LP, such that the difference between f and your new function f or g in LP norm, so I should just put a p, this is smaller or equal to epsilon. G is a continuous function in LP. So this is this notion of density you can approximate as precisely as you want. And the proof is in 3 steps. First, for any f, you approximate it by a bounded function because such a f can be unbounded. Then you approximate this bounded function by a simple function. So it's a sum of characteristic functions. So you make it with characteristic function. A simple function looks like this. Okay. And then you approximate such function with continuous one. So it's in 3 steps. If somebody wants to work on the details, I would be happy. It's not so difficult. At least these first 2 steps are not so difficult. Then I gave the definition of a Hilbert space. So it's a vector space. You have like Rn, except that it is complex. So the scalars are complex, but you can just think about real if you want. There is a scalar product. So when you take 2 vectors, there is an operation which gives you a number. This scalar product is positive in the sense that when you take 2 times the same element, you get something which is bigger or equal to 0 and 0 if and only if f is 0 itself. So it allows you to define a norm. And so a Hilbert space is a complex vector space with a scalar product which gives you a norm. It is complete with this norm. It means whenever you take a sequence, a converging sequence, it converges inside the space. And we also assume that it has a countable basis, so you can just take first vector, second vector, third vector, and so on, even if it goes up to infinity. An example, Cn is the main example of a Hilbert space, which is finite dimensional. Now this L2, the set of square integrable functions, so we define it when we define LP spaces, square integrable function on a set omega. This is a subset of Rn. But you can also do small L2 of n or small L2 of Zn. These are sequences. So this is an element here is of the form A1, A2, A3, and so on. Each of them is just a complex number. And you have the condition that the sum J of Aj modulus square. So when you sum, or if it is real, you just sum the absolute value. If it is complex, you sum the modulus square is finite. Now you can wonder why 2 is so important and not p different from 2. It's because of Hölder inequality. If you check Hölder inequality, you have a p and a q, and they are equal if and only if they are equal to 2. Then I mentioned 4 inequalities, which are very useful in a Hilbert space, in any Hilbert space. And I said if somebody wants to check and prove these inequalities, it's not so difficult, and it's written in many, many textbooks or on internet. And then I introduced this notion of strong or weak convergences. You have 2 different ways of saying when a sequence of elements of H converge to something, either in a strong sense, but the strong sense employ only the norm, or in the weak sense, if you use the scalar product. Yes.
That omega is a subset of Rn and Cn.
No, because I introduce LP spaces on omega in Rn. Of course, we can also take a subset of Zn, but then I would write small L2 of omega if omega. No. It's functions on a subset of Rn with value in C. Yeah, so L2 of omega, let me remind you, this is a set of functions from omega to C. This is a C, so that F is Lebesgue measurable, and the integral of f of x squared dx, when we integrate on omega, is finite. We can also define function on Zn, but this is much more advanced. Sorry, on Cn, but this is much more advanced. Okay, any question or remark? So today we continue with the study of Hilbert space and then operators acting on Hilbert space. I will explain what it is. First, I would just want to state one small lemma, because I said these two things are not the same, and you can check. Strong convergence implies weak convergence, but the opposite is not true. So you can wonder, how can I make an equivalence? Of course, you cannot, but you have this lemma, which makes a comparison between weak and strong convergences. So we consider Fj a sequence in H. And I consider also F infinity, which is one element of H. Now the claim is the following. Then the limit when j goes to infinity of Fj is F infinity in the strong sense. So remember, the strong sense means I consider Fj minus F infinity norm, and this has to go to 0. This is equivalent to, so this is a statement, weak limit j goes to infinity of Fj is equal to F infinity. But of course, I cannot stop here, because if I stop here, it means these two notions are equivalent. So it means there is a second condition. And the second condition is that the limit j goes to infinity of Fj is F infinity. So you need these two conditions. The weak limit, and the weak limit, remember what you compute is something like this, Fj minus F infinity, but you do it on a scalar product with a g. So if this goes to 0 for any g, it's a necessary condition, but it doesn't tell you the fact that this goes to 0 doesn't tell you anything about the norm. And the statement is, if you have this weak convergence plus a conservation of the norm, then this is equivalent to strong limit. And it's not a difficult exercise. It's quite interesting because you can understand what is really the difference. So if somebody is interested, you can check why you need this second condition. And the proof is either fully given or partially given in the notes. It doesn't matter that you cannot work on it as an exercise. If you understand it and write a report on it with your own words, this is very good. All right. Let me now move to subspaces. So we have a Hilbert space. It's a big space. I want to define a subspace, like if you have R3. A subspace of R3 is, for example, just what is on the floor. This is a subspace, or you can take an arbitrary plane. This is also a subspace in R3. A plane is or a line is a subspace in R3. So we have the same notion in a Hilbert space. So this is the definition of subspace. And I use the letter curly M, a subspace M inside H is a linear. I will explain it's a linear subset of H. What is the meaning? Meaning that if you take two elements in M and you take a lambda in C, then F plus lambda G is also in M. This is a notion of linear subset. You can do linear combinations and you stay in the same subset. So this is the definition of a subspace, and M is a closed subspace. This is more interesting, closed subspace. We have already seen the notion of closed with topology. But essentially, this is for finite dimensional spaces. Here, the Hilbert space is often infinite dimensional, so we need a more precise notion. So it's a closed subspace if whenever a sequence whenever you take a sequence and it converges to F infinity in H, sorry, a subsequence in M. Then F infinity is also in M. So let me explain the meaning. This is a notion of closed subspace. And you always keep in mind Q and R. Take a sequence in Q. The limit is not always in Q. You can find a sequence converging to pi, and pi is not in Q. So here it's the same. Take a sequence in M and assume that it converges in H, and we know it converges in H because H is complete. It's a big space. Then it's closed if the limit is in fact in M. Like, of course, this picture is misleading, but take a sequence of points on the floor converging to a F infinity. It's closed if the F infinity is also on the floor and not outside, which is quite natural. So this is a notion of closed subspace, or in other words, M contains its limit points. This is called limit points. But this should remind you what we have done in topology, because a closed ball and an open ball or closed ball have exactly this property. Take a closed ball. So it means with a boundary. Take a sequence converging to the boundary. If the limit is, if we consider a closed ball, the limit is inside the ball, inside the closed ball. If we take the open ball, so without the last layer, then the boundary, this point would not be inside. So it's the same idea. A closed subspace is whenever you have a converging sequence, the limit is inside the set. So try always to keep in mind a few examples, even if we are dealing with infinite subspaces or infinite Hilbert spaces. And just a remark for information. Any closed subspace of H is itself a Hilbert space. What do I mean by this? If you take only the floor in this three-dimensional space, you have also a scalar product only on the floor. You have a norm, which is a two-dimensional norm. So you have also a Hilbert space here. Okay. So it's the same whenever you have a closed subspace, you can do linear combination. You can define the scalar product because you have the scalar product from the original Hilbert space. Because it's closed, it defines exactly a Hilbert space. So this is quite natural. So when you take the restriction on a closed subspace, you have again a Hilbert space. Yes?
Does zero not have to be inside this? I think zero must be inside this subspace.
Look, if I just take everything is equal to 0, it has to be inside. Take, as soon as take G is minus F. If you take G is minus F, so as long as you have an element, you can multiply it by any scalar and the 0 is inside. Okay. So yes, fair. 0, the point 0 is always in any subspace. So when I did the first picture with any plane, it has to go to 0. It has to go to 0. You cannot take an arbitrary line in R3. It has to be a line going through 0. Okay, my picture was misleading. Yeah, 0 is always in any subspace. Examples. I want to have a few examples of subspace and closed subspace. Take a finite family, F2 up to Fn inside H. Any collection of n elements. They can be linearly dependent or not, doesn't matter. Just take n elements in a Hilbert space and set what we call vect of F1 up to Fn. What is this? Just a set of linear combination. This is the set of lambda 1 F1 plus lambda n Fn for any lambda 1 up to lambda n complex number. So this is a vector space generated by these n vectors. By definition, it's a vector space. It's a subspace because it's stable under linear combinations. This vect of F1 up to Fn is in fact, it's even closed. It's a closed subspace. Why is it closed? Because it's finite dimensional. You can try to write a sequence. You will see that it's closed. I let you do it as an exercise, but it's always true. Another example I already mentioned probably last week, the set of test function we have seen in chapter 1. This is inside L2. This is a subspace. Why? Because the sum of two test functions is a test function. Test function, remember, it's a very smooth function with bounded support. if you add two functions like this, or if you multiply one function by C, it is still an element of D. Is it closed? Can you tell me if it is closed or not? Can you take a sequence in this set of test function? If you take such a converging sequence, does it converge inside D or not?
Yeah.
Okay. Somebody else? The answer is no. And you should know it. I mentioned, okay. What I mentioned, I already mentioned this idea of dense. In LP, I said you can approximate any element of LP, so in particular of LP, of L2 with an element in this. So it's not closed. But it is not closed. I just write a sentence, doesn't matter if it is not clear. The closure is L2 of I. So it means if we don't know what is a closure, but you can imagine you want to take all these limiting points, what you get exactly L2. So it's dense, but it is not closed. And the same, you can replace this by the Schwarz space, which is slightly bigger. Schwarz space, it's made of this function going to 0 faster than any polynomial. It's still a subspace because if you add two Schwarz function, it's still a Schwarz function. Or if you multiply by 23, it's still a Schwarz function, but it's not closed. I will recall the notion of density, the precise definition in a second. But now there is something which is a little bit surprising. This is the third example. For any subset inside. What is the difference between a subset and a subspace? A subspace, you have to be able to take linear combination. A subset, no need. This is a subset of R2. If you take this element plus this element here, you are probably moving outside. So this is a subset. It's not stable for addition. A subspace is stable for addition. So take any subset and set what is M orthogonal. So I need to define it. It's a set of F in H such that notion. Yeah, the scalar product between F and any element of M is 0 for any G in M. So you take the set of elements which are perpendicular to all elements of M. This is a definition, and it turns out this is a closed subspace. Even though I started just with a set, probably you can take any set on the floor. What is perpendicular are only vectors going up, and you generate the linear space, which is a set of vertical vectors. This is, you can show it as an exercise. It's not difficult to take this as a definition. Now, if you take two vectors, F1 plus F, if you take a F1 and F2, which satisfies this, the linear combination will also satisfy this. The point is, if you take a sequence of Fj satisfying this, you have to check that the limit satisfies also this. But you cannot generate something different from 0 if you have only 0 everywhere. So it's a nice exercise It's not difficult. You just need to understand the definition. As I said, I just want to recall the definition of dense. I'm not sure I gave it in the past. It's just a remark. Oh, yeah, it's related to this. So reminder. A subset M inside H is dense in H if for any F belonging to H and any epsilon bigger than 0, there exists a G inside M such that the difference between F and G is smaller or equal to epsilon. Okay, I don't remember if I gave it or not. This is a notion of dense. You can approximate as precisely as you want. So sometimes it's misleading because if this is H, of course, it's just a picture. What is a dense set? You need to find points which are close to any element of H. So like Q inside R. Every element of any real number can be approximated by a rational number. So Q example, Q is dense in R. This is this notion of dense. Right? Okay. Now a small exercise related to this and this notion of density. Probably the exercises in this section are much easier than the one on Lebesgue theory. Exercise. M inside H is dense in H. Sorry?
No, I thought that was R.
No, this is M. Okay, sorry.
Sorry. I thought that was R.
M is dense in H if and only if what is orthogonal to M. Can you guess? Something is dense if what is orthogonal. It's not dense, this is true, but this is not. It's just 0. You know, if it's dense everywhere, what is orthogonal can only be the 0 element. Try to think about it. I'm not sure we can think about this, but so this, yeah, you have 1 or 2 exercises which are not so difficult. Is there any question? So this notion of dense, this notion of orthogonality. Of course, in Rn, you are familiar with this notion of orthogonality, but now we have something similar in a space of any dimension. Let's move to, yeah, there is a very nice result about Hilbert spaces, and I want to state it. Dual. Did I already speak about dual space? Maybe I did not pronounce this name, did I? Probably not. Okay. But this is something, in fact, you already know it. It's something important. So let me first give you the example you know. The dual of D of Rn is the set of distributions. I did not define dual, but I will do it. But I can already tell you one example. The dual of Rn, the test function, is a set of distribution. And the same, the dual of the Schwarz space is the set of tempered distribution, f prime of Rn. So you already know two examples of dual. The dual of this space is this one, the dual of this one is this one. So what is the dual? Dual is the set of linear functions on a space with value in C. I have to be a little bit more precise, but indeed, remember the way we introduce distributions. They are taking test function and they send it just to a number. So it's a set of linear, and it's linear. In the sense, if you take a linear combination here, then the result is also linear. So it's a set of linear function on a space, this one or this one, with value in C. That's important. And there is one more thing, which are continuous, which is a set of linear functions, which are continuous. And indeed, I had to assume some continuity. I said it with some convergence. When I introduced this, it was with the notion of convergence, but in fact, it corresponds to continuity. It's not it's more or less a precise definition of a dual. So now you would like to know what is the dual of a Hilbert space. So what is the dual of H? So I will give the precise definition. So I would like to have, because H is a vector space, so I can define the set of linear functions from H to C, like we did it here. So, and we denote it by H. It's not a prime, it's a star. This is the usual notation. H prime, let me give you the definition. It is a set of phi function from H to C. H star, no, I said usually we use star for this one. This is a convention. But indeed, I could use prime, but usually we say H star. Such that, as I said, it has to be linear. So whenever you take F and G in H and lambda in C, one has phi of F plus lambda G is phi of F plus lambda phi of G. This is a linearity. And now I want some continuity or something like this. And phi of F, it's just a complex number. So I can take its modulus is smaller or equal to a C times the norm of F for some C bigger than 0 and all F in H. This is a definition of the dual. Linear function, but you need a continuity or some boundedness. There exists a C such that this number, it's a complex number, take its modulus, it's smaller than this C times the norm of F. And of course, if it is bounded like this, I can even give I can use this to give a norm on phi. So we set, so for phi in this space, we set what is the norm of phi as an element of the dual. You can guess. You want to take the minimal value of C. So it's exactly this. Okay, I'm writing something different, but these are equal. Right. I said you want to take the minimum, and I brought them supremum. Oh, be careful, the camera. Okay, let me check. No, we can still see everything, I think. No, that's okay. No, there are just two pictures. You know, we have C, and I compute phi of, no. Either, so you have to wait to think about this. Either you take the smallest one which satisfies this, or you go from below. You take all the one which do not satisfy, and as soon as it is satisfied, you take the maximum value. So, or this is equal, I can give both. This is also equal to inf over C belonging to, or C bigger than 0 of the set phi of F smaller or equal to C times F. If you think about it, these are just, you get the same for the same value for all F. Of course, F is different from 0. You can either take a supremum from below or an infimum from above. So I'm giving a value, a norm to this. Okay, so far this is just a definition. Take the set of linear functions satisfying something, and I just associate a positive number. Now you can wonder, oh, how is this? I mean, it was very complicated. Here we went from test function to distribution, from Schwarz function to tempered distributions. It turns out that, let me just state first the result, but then I will justify. Theorem H dual is the same as H. You don't get anything else. So let me explain this. It's not a proof, but idea. Take any G inside H and set phi with the index G of F is this scalar product. I define what is going to be an element in the dual. We don't know it yet, but I define this. Yes. Wait a second.
Any linear function that goes to a closed subspace?
No, just any linear function from H to C. That's it, which is bounded. So I need to check. Indeed, I'm claiming claim phi G is an element in this space. Check it. Phi G of F1 plus lambda F2. I take F1 plus lambda F2. This is scalar product G F1 plus lambda F2. Now you know the scalar product is linear. I took it in the second argument. So it makes scalar product G F1 plus lambda G F2. But now by my definition of phi j, this is first condition. This is equal to phi j of F1 plus lambda phi j of F2. So the first condition, the linearity condition, is satisfied. What about the second one? Observe that phi j of F, I'm claiming that this is always smaller or norm of G, norm of F. Do you agree with this? We know this scalar product, if you take its modulus, it's smaller than the norm of G, the norm of F. But now, if I take F is equal to G, I'm allowed. G is an element of the Hilbert space, so I can just take F is equal to this one. One has phi j of G. It is GD, which is the norm of G squared. And probably I should write it is the norm of G times the norm of G. That's it. Okay. So what does it mean? It means that the C I was computing here is exactly norm of G, which means that the norm of phi G, sorry, in this space has to be this number. You have no choice because you have an inequality, so it means the C is at most this one, because you have to take the minimum value, so at most it is this one, but you cannot take smaller than this one because you have it here. So the conclusion is that we have proved the claim here. Any vector of the Hilbert space define it's called a linear functional. So the conclusion of this small computation is that the conclusion is any G inside H defines an element which I call phi G of H star, right? And now this is not sufficient in order to have this theorem. What else you have to show is that there is no other one. So the claim, which I don't prove, but it's a little bit long. Claim all phi belonging to H star are of the form phi is a phi G for some G inside H. So you can generate all of them. And if you have this, you understand this theorem. Any G defines, I did not write it, but this is also called linear functional. Linear, it's clear by definition. Functional means function with value in C. So you see with Hilbert spaces, you don't get a lot by looking at this. For test function, we got distribution. For Schwarz function, we got tempered distribution. For Hilbert space, you just get it the same Hilbert space. But this will be important. What is the name of this result? It's Riesz lemma. It's an important result, Riess lemma. I will come back to this a little bit later. So if we summarize what we have already seen today, we have introduced this notion of subspace or closed subspace. This is important. And I introduced this notion, the notion of orthogonality, and we have introduced this notion of a dual. But for Hilbert spaces, the dual, it's called a dual, the dual of H is H itself. I don't write an equality because I have to go from this to this guy, but it's a one-to-one correspondence. So it's more or less the same. Like H goes to TH when we discuss distributions, it's a one-to-one correspondence. It's identification. So we can move to the next section, except if there is any question. In fact, this is going to play a very important role in a few minutes. Otherwise, without this, you cannot do quantum mechanics. I'm sorry. So you need this result in order to play with quantum mechanics. Even if nobody is, John is probably not saying that quantum mechanics is based on Riess lemma, but this is a fact. I will come to it. So next section, 3.2, bounded linear operators. So far we have seen Hilbert spaces. The Hilbert space is a vector space with a scalar product and some properties. We have seen anything. What is a bounded linear operator on it? It's like a matrix. In fact, H, the simplest example of H, I already mentioned, this is the simplest one. So what is going to be a bounded linear operator? The simplest example of this, it's a matrix. Mn of C, it's a matrix because it takes an element of Cn and sends it to a new element of Cn. But of course, this is baby example. Linear algebra is a baby example for this course. I want to deal with any Hilbert space, so it can be of dimension infinity. So you have to replace matrices by bounded linear operators. So I need to define this. First, linear. Linear is always something simple. So let M n be vector space. Vector space, you can do addition. Vector space. A linear operator T from the, oh no, B, I changed the letter. B. From M to N, you can guess if it is linear, it means that it satisfies B of a linear combination, B lambda F plus lambda G is BF plus lambda E G. By the way, is this the same plus? Or are they different?
It's definitely different.
It's definitely?
The BF plus lambda B.
It's in this space. This plus is a plus, is the addition in this space. Now, this plus is in this space. So they can be different. It's a linear, I mean, you have in any vector space, you have the notion of addition, but they can look differently. They can be different because this plus is you add two elements here. Here, BF is already an element of N, BG is an element of N. You do a linear combination in this space.
Sorry, that's not definitely, but it's not the same.
It's not this. There is no reason why they should be the same. In general, they are not. Just to remind you.
It's in general.
In general, yes. Okay. Yeah. Matrix. This exists. You can have matrices of operators, but it come later. It will come later. Don't worry. I haven't defined an operator yet. But yeah, if this is Cn, this is Cn, a linear operator is just a matrix. Now, let me give the precise definition of a linear operator. I just a bounded linear operator. Here I define linear operator. Definition. A map or function. For me, map or functions are the same. B from H to H. So from one Hilbert space to the Hilbert space itself is a bounded linear operator if, of course, B of F1 plus lambda F2 is B F1 plus lambda BF2. This is just the linearity. And what means bounded, that it is bounded, and BF. BF is an element of the Hilbert space, so I can take its norm. Small or equal to C times the norm of F for some C bigger than 0 and all F in H. This is a bounded linear operator, nothing very special. Linearity, boundedness. What is the notation for the set of all bounded operators on H? B of H, yes. Still in the definition, the set of all bounded, all matrices, if it is finite dimensional, the set of all bounded operators on H is denoted by B of H. B for bounded. Be careful, it's not the same B as this one. This is one operator, and this is a set of all bounded operators. And in some books, all books, it's also written simply L of H, but I think now it's old-fashioned, just L is for linear. But in some books, they assume that it's bounded as well. I can still write it in the definition for B inside B of H. So for bounded linear operator, we set the norm of B. Be careful, yeah, this is misleading, but everybody uses this convention. I'm going to define the norm of B with the same notation as the norm of the Hilbert space. So don't be confused. These two things are not the same. They are not equal. This is a norm of a vector of the Hilbert space. This is a norm of a bounded linear operator. I know it's the same notation, but this is what people used to do. So what is the definition? The same as I did before. It is either the sup of this BF divided by F for all f in H. F, of course, different from 0. This is if you go from below, but it is also the inf over all C bigger than 0, such that BF in norm is smaller or equal to C times F. These two things are the same. I already mentioned this before. For any F in H, I should write any F. This is the size of your matrix, but we are dealing with more things more general than matrices. So be careful. We use the same double lines for the norm of a vector and the norm of an operator. That's a convention. So examples, I already mentioned matrices. So let me write it. Examples. This is the first one. If H is just C or N, then B of H, which is the same as B of Cn, is simply the set of n by n matrices. Nothing. Complex valued. Your matrices are complex valued because the vector space is complex valued. But something probably new. If H is L2 of omega. Remember, these are functions defined on omega, or you can take R. Let's take Rn. Functions on Rn, which are square integrable. What is a bounded linear operator? An example. So I want to take such a function and come back to a square integrable function. So there is one class, we are going to see different classes, but one class of bounded linear operator. For any, which letter? M, also from Rn to C, bounded. So for any function from Rn to C, I'm going to set please be careful because I'm going to use this example many times. Set B index M. Why B? Because I want to deal with bounded operators, so I use B, but it's defined with respect to M, so I put it as an index. B on a F. What is F? F is an element of the Hilbert space. So now I should get a new element of the Hilbert space. So a new integrable function. So this is a function. I can evaluate it at X. X is a point in Rn. Definition, just take the multiplication. You don't have so many options. You multiply these two functions. You have one function which is a function on Rn, but which is L2, and we have one function which is just bounded. You multiply them. I want to be sure now that it's well defined. So check. The first one is easy. Bm on F1 plus lambda F2. Let us do very carefully. Evaluated at X. This is M of X, F1 of X plus lambda F2 of X. This is M of X, F1 of X. This is just a multiplication of numbers plus lambda M of x f2 of x, which is nothing but bm f1 evaluated at x plus lambda bm f2 evaluated at x. So what you observe, this is equal to this guy plus this guy. So the linearity is clear. The point is it bounded? So what I need to check, so this is the first check one, now check two. I need to check that question. You have to check that this BMF is indeed in L2 of Rn, because this should bring you back in the space and check that it's bounded. So let's compute the norm. What is the norm of BF? I can put a 2 just to remind you that we are dealing with L2. This is the integral of BMF by definition at x squared dx. I should take a square root. I don't want to take a square root, I'm lazy. So it's the same, it's easier to put a square here. Or otherwise you put square root everywhere. But I compute this norm square. Okay, now I know the definition, integral of m of x, f of x, modulus square dx. Okay, and what can you do with such an integral? You know that m is bounded. So you take the maximum value. This is smaller than sup over y belonging to Rn of m of y. I need to take a square because everything is square times this integral of f of x squared dx. You should know this. You have an integral, you take the maximum value of this guy, and you take it outside of the integral. You can check. And what is this number here now? This is the norm of f squared. This is nothing but the norm of f squared, right? And this is finite, this number. In fact, I already gave a name. I gave a name to this. This is the norm of m infinity. I gave this name. So we get norm of bm on f, L2 norm is squared. So the conclusion is that we have obtained that the norm of Bm on F, the norm of the Hilbert space, so I can even delete it, is smaller than the norm of M infinity times the norm of F. And there are many norms, so be careful. This is the norm of the Hilbert space. Norm of L2 of Rn. And the other one is L infinity norm. I have introduced last week essential sup norm, but here you can just take the sup norm. So this is the fact, this is a proof that this operator is bounded. So we get a linear operator which is bounded. So it means Bm is a bounded linear operator on L2 of Rn. And it has a name. These kind of operators are called multiplication operators. It's not the only possibility, of course. This is just one type of operators. But it's very useful to have this in mind because it's very different from a matrix. Why is it so different? Because first, the Hilbert space here is not finite dimensional. You don't have just a basis which is finite. You need to go up to dimension infinity. And this Bm doesn't look like a matrix, right? But still, we have shown that it's a bounded multiplication operator. Any questions? This is probably the first time you see this kind of operator. So please, it will come back. Be careful about this. Next exercise, but you need to check on Wikipedia if you want to do it. B of H is a normed algebra. I haven't defined algebra. You probably know what it is. It's a vector space, but it has a property. You have a multiplication. Indeed, B1, so you take a first of B2, B1, which is a second bounded operator on F, like a multiplication of matrices. I can define this as B2 applied to B1 applied to F. So you have this multiplication, and you need to check a list of properties, but it's like product of matrices. And what here means normed, it means B1, B2. I can take its norm because it's again a bounded operator. It's smaller or equal to the norm of B1 times the norm of B2. You can check it from the definition of norms. So this is something you can check. You have this product for bounded linear operators, so you need to check that this is again linear, but it's quite simple, and you need to check this inequality from the definition of the norm. So this one is easy. Let me state a second exercise, which is slightly more difficult, but it's quite useful to have this result. If somebody third or fourth year want to do it, I would be happy. If M1 and M2 are dense subspace of H, I have introduced this notion of dense on subspaces of H, then you can compute the norm of B. And B is in B of H. B is in B of H. Take a bounded operator. There is a formula sup over all F in M1, norm of F is 1, sup of all G in M2, norm of G is 1, of B F B G. So what does it mean? It means you can compute the norm of F, you can compute the norm of B by taking just scalar products. So you take scalar products between F and BG, but you now take all F on a dense subset, all G on a dense subset, You take the maximum value, or more precisely, the supremum, and you get this number. So it's not completely trivial that you really get an equality, but it turns out to be true. And this is interesting because, in a sense, think about this already for matrices. You can think about this already for matrices. What is the meaning of this for matrices? I gave a definition of a norm for matrix. I do it with a scalar product, and you need to check that you have an equality. If you understand this for matrices, it's already good. So this is a useful formula. You can do it. Now I said Riesz lemma is very important because on B of H, you have one more structure. One more structure. On matrices, there is one thing I didn't mention so far. What do you have on matrices? What can you do? What kind of operation you can do on matrices? Yes, addition. Yes, multiplication. Yes, yes. In the algebra, you have also an addition. What else? Taking? No, you cannot do it for arbitrary matrices. You cannot take the inverse of the zero matrix. Transpose, this is correct, but even you can do better than this. You can take the conjugate. Why transpose is not enough? Because transpose is fine for matrices with real entries. Now I want to take matrices with entries in C. There is this notion of conjugate. So I will come back to it. One more structure on B of H. It's called an involution. So let me explain definition. For any B bounded operator on Hilbert spaces, there exists a unique B star, which is also a bounded operator, bounded linear operator, such that, and this has to do with the scalar product, FBG is equal to B star FG for any F and G in H. This is the, it's called the adjoint. B star is called the adjoint. So now for matrices example, for the Hilbert space Cn, B of H, just and by n matrices, what is now matrix? I'm going to define it as a collection of Bij with I on j from 1 up to n. This is a matrix with entry Bij. What is, so this is B. What is B adjoint? You need to take the transpose, as you said, but also complex conjugation. So this is a collection of Bji complex conjugation on J. So it's complex conjugation. complex conjugation. And here you take the transpose. So if you deal only with real matrices, you don't have to take the complex conjugation. You just take the transpose, but we are dealing with complex matrices. And you can check that for this operation for matrix, you have this equality. How do you prove that there exists a unique B star? This is Riesz lemma. Based, I don't give the proof, but it's a standard one based on Riesz lemma. So you use Riesz lemma to show that there exists for all Hilbert spaces, there exists an adjoint for all bounded linear operators. All right. So this Riesz lemma is very important because of this adjoint. Some properties. No. Is there any question or remark? So if it's hard for you to imagine what is going on, always think about matrices. But what we are doing can be done in, or we do it in infinite dimensions. So the n here can go up to infinity, but in fact, when you go to infinity, you are dealing with L2 spaces. By the way, at the beginning of quantum mechanics, they dealt with matrices of size infinity times infinity, and it was not fully understandable. And then they end up with this notion of L2 spaces and Hilbert spaces. So in the history, you have at the very beginning this notion of infinite matrices, but also Hilbert spaces, and at the end, everybody is speaking about Hilbert spaces because this is the right framework. But it's an extension of very big matrices. Some properties of this involution. This is also called an involution for the following reason. So properties. I take two elements A and B bounded. What is the norm of the adjoint? Yes, excellent. How do you show it? Remember, I have written just before this equality as dg. Take the supremum over all. But with this formula, it's very easy because by definition, you can put the adjoint here and you get the same formula. So you get this equality for free. From this, the formula I have written, you directly get this equality, yes. What is B star and then star again? Yes, you get back to B, and this is why it's called an involution. If you do it twice, you're back to your starting point. Then what is the norm? This is slightly more difficult. But this is very, very important. In fact, this is a full subject. This is called the C star property. It's called C star property. You have books on C star algebras. So this is very important. So the norm of B star B is the norm of B square. And the number 4 that you probably know for matrices, what is AB adjoint? It is a product of the adjoint, but in the reverse order. Be careful about this. You can prove these things. This one is slightly more involved, but these are very simple. what about our multiplication operator? Can you guess? I introduced this multiplication operator. What is the adjoint of this multiplication operator? Try to guess. So I just recall the framework. Example. I recall that H was L2 of Rn. And this bounded operator was multiplication by M. So can you guess what is Bm adjoint? Try to imagine you put it in a scalar product. So what you have to compute is Bm on a F scalar product with G. By definition, this is Bm adjoint on G. Yes, this is by definition of the adjoint. Now, what is the scalar product? This is the integral on Rn of G of X complex conjugate, and this, so you have M of X, F of X. I want to have something here. So what do I need to do? Say it again.
MP bar.
Not multiply.
Well, I want to multiply, but so the operator dm star will apply when applied to G will give us MP bar.
Yes. So what you can do, you can take complex conjugation and take it again, because taking 2 times the complex conjugation is doing nothing. And now I can write it as integral on Rn of G of X, M bar of X, bar. I have exactly the same thing. F of X, X. And now this, you should get the result. This is going to be, and this is what you wanted to say, Vic. This is nothing but B M bar G F, because check M bar is a function M complex conjugate. If you compute this right-hand side, you get exactly this by definition. So it means Bm star for multiplication operator is just the multiplication by the function complex conjugate. This is a proof. So in B of H, we have this notion of involution, which is very useful. And this adjoint is at the root of quantum mechanics, because in quantum mechanics, you study self-adjoint operator. I will come to this next week. I still have a few minutes. Convergence in B of H. You remember in H, we had already 2 notions of convergence. I recall it at the beginning. We had the weak and the strong convergence. On B of H, I think you can define 16 notions of convergences. We are going to mention only 3. Yeah, there are many. 3 main types of convergence. So the definition so be careful. I'm considering a sequence of bounded linear operators. So it's like a sequence of matrices. I consider a family of matrices, and I want to say that this family is approaching a certain matrix. So I consider a sequence in B of H and B infinity, also an element of B of H. So you can guess 3 types of convergence. Bn or Bj converge to B infinity uniformly if Bj minus B infinity takes a norm, goes to 0 when j goes to infinity. That's a natural notion. You take the difference of these 2 operators, it's a vector space, so you can take the norm and you assume that this norm goes to 0. This is the strongest notion of convergence. But you can do something weaker. Then you will feel the difference. And sorry, I need to write. We write U with limit j goes to infinity of Bj is B infinity. So this U is for uniform. The second notion is this family Bj converge strongly. Before it was uniformly, now it's strongly again, strongly to B infinity. Who can guess something weaker than this? So far, I have not used the elements of the, no, not scalar. I haven't used the notion or the elements of the Hilbert space. So I can do it. Converge strongly to B infinity if for any f in H, norm of Bj minus B infinity on a f goes to 0 when j goes to infinity. What is the difference? If you remember, this is just a notation. It means for any epsilon, you can find a capital N such that this difference is smaller than epsilon. But the capital N can depend on f. Here, we don't have this freedom. The capital N depend only on Bj on epsilon. Here, you can find the capital N as a function of f as well. And in this case, we write strong limit j goes to infinity of Bj is equal to B infinity. And now the third one is to use scalar product. So Bj converge weakly to B infinity if now you take 2 vectors for any fg in H. The scalar product between f on Bj minus B infinity on G goes to 0 as j goes to infinity. This is just a convergence of numbers because look, this is just a number. And in this case, we write the weak limit j goes to infinity of Bj is B. This notion of convergence probably will not play such a big role, but it's important to know when a family of matrices converge to something. But for matrices, they are all equal. So be careful. When it's finite dimensional, for H is Cn these 3 notions coincide. So you don't get anything. Interesting. So it means you can feel and you can see the difference only if you are in an infinite dimensional space. Otherwise, you have no way to see it. Can you guess which one is the stronger one? It's easy, but uniform. Because you can check that 1 implies 2. And 2 implies 3. Why? Because let's check the first one. If you want to compute bj minus b infinity f, you already know that this is smaller or equal to norm of b. By definition, oh, maybe I didn't emphasize, but this is by definition of the norm. So if this one goes to 0, of course, this one goes to 0. And the same if you take f bj minus b infinity on a g, you want to compute this, but you know that this is smaller than norm of f time norm of bj minus b infinity. You know this. This is Schwarz inequality. So if the right-hand side converges to 0, the left-hand side also converges to 0. So the strong limit implies a weak limit. So this is U implies S, uniform implies strong, strong implies weak. All right. Exercise, but you have to go to infinite dimensional space. Show that the converse is not true. And how do you show something is not true? You find a counterexample. This is the easiest way. If you find a counterexample, then you are done. So exercise, I'm sure you can find many examples on internet. Exercise. Find an example of weakly convergent sequence, which is not strongly convergent. Sequence which is not strongly convergent. In fact, this is not so difficult. So it means if you find an example like this, you show that weak doesn't imply strong if you find a counterexample. But you can also find of one strong which doesn't imply uniform. So if you find an example of a sequence which converges weakly but not strongly, or if you can find a sequence of strongly convergent sequence, but which is not uniformly convergent, then you have shown that these three notions are different. Okay, you can even, again, don't do it for matrices. You will not be able to do it for matrices because it's not true. It's the same. But you can probably think about the multiplication operator I have introduced. So you need a family. Consider family B, M, J, a family of functions. And what does it mean that it converges weakly or that it converges strongly? It's not trivial, but if you understand this, you understand a lot. So even if you don't get a full example, but already try to understand what it means, you will learn a lot.